Okay. Let's do some more examples of nice arrangements and nice characteristic polynomials, etc. So the first thing I wanted to do is revisit the Braid arrangement, which I forget exactly what I called it, but now I'm going to call it A2. And this is an arrangement it really lives in 3 dimensions. The hyperplanes are x1 equals x2, x1 equals x3, x2 equals x3. And as you guys already know, this is really a 3-dimensional picture that kind of comes out of the board like this. And it's kind of, this is like a cross-section of that picture. Okay? So this is A2. Now, this is the arrangement that you guys did for your homework. It has the hyperplanes x1 equals x2, x1 equals x3, x2 equals x3, and x1 equals minus x2, x1 equals minus x3, and x2 equals minus x3. Okay. So, and you'll see why in a second, but I'm going to be calling this one D3. Okay. So there's a couple of things that these pictures have in common, and that's what I want to briefly discuss. So imagine that imagine that this is a bunch of mirrors, okay? So each wall is a mirror. And now maybe you're standing here and this is you have your eyes right here and you're facing this mirror, okay? So then you're going to see a reflection of yourself, and that's right here, right? It's looking at you. Now, is there anything else that you see? Well, if you kind of look over with your left eye carefully, you're going to see that there's another image of yourself right here, looking this way, right? Which is the reflection across this mirror. Okay. Okay, but now you're going to see more. There's more copies of you because, for example, there's the reflection when you look this way and then see your reflection of yourself in the mirror right here. Okay? And that's really coming from reflecting this across this mirror, and now it's looking this way. Okay? So you see, if you look in this direction, then you're going to see this reflect into this, reflect into this. And you're going to see something that looks like this, but it's really a reflection of yourself. Okay? Same thing if you look this way, you can find a copy of yourself from this mirror to this mirror back to yourself. And that's coming from the reflection of this guy across this mirror. Okay. And then finally, there's another one here. Okay. By the symmetry of the picture, you know that these are 60-degree angles. And if you really go to your house and you do this and you put 2 mirrors at a 60-degree angle, you're going to see that you're going to see 6 copies of yourself. You're looking at yourself, and then there's going to be 6 copies in the mirror corresponding to these 6 copies. Okay? 1 copy per region of the arrangement. Now, we have a different way of thinking about this, which is that we have labeled this copy of yourself 1, 2, 3, okay? And now when you reflect across this mirror, you switch the numbers 1 and 2, okay? And when you switch across this mirror, you switch the numbers 2 and 3. Then here you cross the mirror 1, 3. Sorry, this is always very easy to get wrong. So I'm switching positions. Okay? So here, I mean, the way that you can think about this is that this is the point 1, 2, 3. Okay? Imagine that you're standing at point 1, 2, 3. Then as you reflect across x1 equals x2, that's going to switch your first and second coordinates. As you switch across 2 and 3, you're just going to switch your second and third coordinates. Now if you switch across x1 equals x3, that's going to switch your 2 and 1 your first and your last coordinate, and give you coordinates 2, 3, 1. Okay? So if you look at the difference between these two vectors, it's the vector 1, 0, minus 1, which is the orthogonal vector to this hyperplane. Okay? Now here you're crossing x1 equals x2, so that swaps your first two coordinates. And here you cross x2 equals x3, so that swaps your second and third coordinate. And you see here, if you go back from here to here, that's swapping your first and last coordinates and so on. Okay? So what's hiding here is, I mean, and we already saw this, that you have one permutation in each one of these chambers. But what you might have not realized yet is that the permutations of a set form a group. And that group is looking at you in the eye right here. That's exactly what's going on here. This right here is the elementary transposition of the second and third positions. This one is the transposition of the first and second coordinates. And the point is that already those two transpositions are enough to see everything, because those two, the transposition of the first two coordinates and of the second two coordinates, those generate the group. And that means that you can just be in a room with two mirrors and you're going to see everything else, just with two mirrors. Okay? This is called a reflection group because it's generated by reflections. Okay, so in general, a reflection group is given by a bunch of hyperplanes, and the generators of the group are given by reflecting yourself across a hyperplane, and then just doing the kaleidoscope thing and just letting yourself reflect all over every hyperplane and seeing what you get. Okay, and if you start with this very nice arrangement, then it's very nice, and you see exactly 6 copies of yourself. Okay. Okay, now this is going to be a challenge, but I think I'm going to try to do it anyway. Let's try to do it here. So how can we look at this picture? This is truly a three-dimensional picture, okay? And so probably I should actually draw the origin here. So that's the origin. And let's maybe, this is going to be impossible. But so this is the center of the cube, okay? And then this is a little region formed by the center of the cube and these 3 points, okay?
Is there a line that goes to the top?
Yes, so there is a line. No, not in this picture. I mean, probably a good thing to do is to look at the homework. Actually, if you happen to have your homework in front of you, that would be very helpful, I think, for you to stare at that picture instead of at this one that I'm going to draw, because it's very hard to draw this picture. But the point is basically that if I ask you to draw the intersection with the boundary of the cube, and that's not too bad. Basically, you just get an X in each. So in each of the little squares, you just get an X. But then the picture is really three-dimensional, and it's really like from the origin, you're connecting to everything. Okay.
Like in each region, are showing you like copies of that.
Yeah, exactly. And so actually, I take back what I said to you too. You're right. I should connect the origin to every point that I see there. And what you're going to get is one of these little wedges. It's a three-dimensional wedge. And you're going to get one wedge in each one of these 24 pieces. And I say 24 because there's 6 faces of the cube, and there's an X in each face, splitting it into 4 pieces. Okay. So that's how you know that this arrangement has 24 regions, and each one is the wedge over one of these 24 triangles. Okay. And I'm just drawing one of the wedges because otherwise it's going to be impossible to keep track of what I'm drawing. But now imagine that we do the same thing that we did here, okay? And this is where I'm getting a little bit worried, but I'm going to try anyway. So imagine that now you're standing in this three-dimensional wedge, okay? and you reflect yourself around. Okay, so imagine that each wall is a mirror. Then you see that there's a mirror image of yourself here, another one here, and another one here. Okay, and image of yourself over here with this mirror, and then basically what you're going to get is just a kaleidoscope where there's going to be an image of yourself in each one of the pieces of this arrangement. Okay. And I don't know if you see that right away. You might have to take my word for it for now and just really draw it and really take the time, look at this picture, reflect it around, but you'll see that you get exactly one copy of yourself inside each one of these regions. Okay. And if you ever wonder how kaleidoscopes are made, this is exactly how they're made. And this is maybe a fun experiment. If you really make a wedge of this shape, so you need to make these two mirrors have a 90-degree angle. You need to have these two mirrors you have to get the angles correct. And if you do that, and if you look inside, you're going to see 24 copies of yourself. So if you go to children's museums, they have this. You've probably seen it at some point in your life. Okay. Okay. And see, I wish I had labeled this ahead of time. I don't know if I can do it on the spot. Can I? Exactly. So really, you only need to be in one of the little wedges, and you're going to see the whole picture. Okay. And again, here there's a group lurking around. What group is that? Well, it's the group generated by whatever these things are, and that's where I wish that I had labeled them before coming here. What are they? I mean, they should be basically. I mean, let me give you an example. This, and this. Those three hyperplanes, wherever they are in this picture, they form one of the wedges. And why do I say this? Because just like over here, and you know what? Let me just try to. So let's say that this one right here is x. This is x1 equals x2. Okay. And let's say that this one is x1 equals minus x2. Okay. And here I could have gotten this wrong, but I think I don't have it wrong because these two things are perpendicular to each other, as they need to be. Okay. And then let's say that this hyperplane right here is x2 equals x2 equals x3. Okay. Okay, and now let's say that I take the point 1, 2, 3 as I did over here. So what happens when I reflect across x1 equals x2? Well, the same thing as before. It just swaps the first and second coordinates and gives me 2, 1, 3. Okay. Now what happens when you reflect across x1 equals minus x2? The effect is that, and by the way, Dilo has been thinking a lot about this in a very different context of Lie algebras. What this does is that it swaps the two coordinates and it changes the sign of both of them. Let's see. So I need to get this right. This is. So I think I need to swap the order and swap the sign of both of them. And if you look at the difference between those two vectors, it's no, I forgot to swap the. I told you I need to swap the order and the sign, and I only swap the sign. I need to swap the order and the sign. And if you look at the difference between these two vectors, it's 3, 3, 0. Okay? And that is perpendicular to this hyperplane. Because the normal to this hyperplane is 1, 1, 0. So now, I swap 1 and 2, So I get -2, -1, and 3. Okay. Now, for example, here I swap x2 equals x3, so that swaps the second and third position. So this is 1, 3, 2, and so on. And I just keep doing it. And if I keep doing it, I'm probably going to make a mistake somewhere. But the point is that if you do this carefully, you're going to get 24 little words in 1s, 2s, 3s, -1s, -2s, and -3s. And what exactly are they? They are the signed permutations of 1 up to n with an even number of minus signs. That's just what you get. And by sign permutation, I just mean a permutation where you can put a plus or a minus sign in front of each thing. Now, you might not know this group, but this is a group. And if you, I mean, and basically these are the operations in the group, just reflecting across these walls. Okay. But again, what's remarkable about this is that this is a beautiful kaleidoscopic gallery of mirrors, so that when you start reflecting around them, you get exactly 24 copies of yourself, and it's a finite number. Okay. And this is called the group D3, the Coxeter group D3. Okay. Yeah, that's a very good point. Okay, so let's talk about another example, maybe an easier example. I don't know. Can you think of another gallery of mirrors that would have this property? This nice property. Let's do it in the plane. So I mean a bunch of lines in the plane that have this nice property. For example, these ones. Yeah. If you start reflecting this around, you're going to get these copies of yourself. Or I don't know. This is harder to draw, but for example, if I were to get the angle right, then this would work out. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, I didn't get it right, did I? Wait, what happened? Oh, and I skipped. Oh, here. Thank you. I reflect over, and it comes here. Reflect, comes here. Reflect, comes here. Reflect, comes here. Reflect, comes here. How many copies? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is the dihedral group of order 10. Okay. 12? 12. Thank you. And why 12? Because I chose this to be an angle of 360 divided by 12. Okay. And if I chose the angle to be 360 divided by an integer, then I'm going to get that many copies of myself, and it's going to be the dihedral group. But if I choose some other angle, then this is not going to work out, and there's going to be infinitely many copies of myself. Like if I chose an angle of I don't know, pi degrees, it's going to be infinitely many copies of you. Okay, so here's a question. What are the finite reflection groups? In other words, what are the possible kaleidoscopes that give you a finite number of copies of yourself? Okay, that's a natural question for aesthetic reasons and also for many mathematical reasons. And we have some examples. So, for example, the dihedral groups. All the dihedral groups. Well, you've thought about the Braid arrangement a lot already, and I think you see how this picture generalizes to any dimension. Whenever you cross the hyperplane xi equals xj, you just switch coordinates I and j, and that moves your permutations around. So that's the symmetric group. And we called it an minus 1. This works out in any dimension also. And this has a name. Is it? There's one called hyperoctahedral, and the other one is called something else. But anyway, so this is something, some group. And there's another infinite family. Very weird ones that are called E6, E7, and E8, and they live in 6, 7, and 8 dimensions, and they're very strange, and they're almost like just how the icosahedron is kind of a freak accident of nature. It's not clearly not an accident, but the icosahedron is somehow a strange regular polytope. Well, this is a strange reflection group. Somehow these are the nice ones. They come in infinite families, and these are just some weird ones that pop up. And that's it. This is the full list of all the finite reflection groups. So there's definitely no coincidence. So if you've taken a course either in Lie groups or in Lie algebras or in Coxeter groups or in regular polytopes, these things come up, and that's why I say there's a lot of mathematical reasons. These objects appear all over mathematics. They're very interesting, and actually, if you're interested, I taught a whole course on Coxeter groups, and it's all on video, so you know where to find it. Actually, maybe. Yeah, anyway. Okay, so you guys know where to find it. If somebody is watching this on video, just go to my website and then you'll find it there. Anyway, so the point is that these are nice finite reflection groups. They have very nice hyperplane arrangements, and we're going to compute them. That's what we're going to do. Okay, and then we use this to check the number of regions. We plugged in -1, and we saw that we got -1 times -2 times -3 up to -n. And if we drop the -n's, you get 1 times 2 times 3 up to n, which is n factorial, which is the order of the group. There's no big mystery there. Okay, but it's nice because that works out nicely. Okay. Let me delay this one for a second, and we're going to get back to it. Instead, let me tell you first about Bn and Cn. Okay, but this was for an minus 1. That works out. It's very nice. What about Bn and Cn? Well, I'll tell you what the hyperplanes are. So they're all of these ones that we have in Dn. So we have xi equals xj for all I less than j. And then we have xi equals minus xj for all I and j. And so far that's Dn. But you also have the hyperplane xi equals 0. Okay? And if you actually I'm gonna draw this in here. So here we have D3. So what am I missing to make it B3? I'm missing, let me first erase what I don't need. And think about where the missing hyperplanes go here. So that's D3. But now we're going to make it B3, which means that we're going to add x1 equals 0, x2 equals 0, x3 equals 0. And as I told you, that is going to drop this condition on the number of sides. Okay? So you see where those hyperplanes go here? They're basically x equals 0, y equals 0, z equals 0. So for example, z equals 0 is that the height is 0. In other words, it's like the equator of this thing. Okay? So that looks like this. Okay? It's like a belt around it. But that's only z, but we need to do it for x and for y. Okay? And so that is B3. Okay? How many regions does it have? (48), right? Because again, we have 8 in each square, and then there's 6 squares, so there's 48 regions around there. Okay, how are we going to compute this characteristic polynomial? We're going to use it using the finite field method. It's going to be the number of points x1, x2, up to xn in fq to the n, such that they cannot satisfy any of these equalities, right? So we need to, and it's kind of like the graph coloring thing. We need to assign a number between 0 and q minus 1 to each one of these guys. But we're never allowed to assign 0. We're not allowed to assign the same number to 2 positions. And we're not allowed to assign a number and it's negative to positions. Okay? So how many ways are there of doing this? Well, how many choices do you have for the first coordinate? It's q minus 1, right? It's q minus 1 because you get to assign any number between 0 and q minus 1 except that you better not use 0. So here you have q minus 1 choices. Now what about here? How many choices do you have for x2? Is it q minus 2? So q minus 3. So why q minus 3? Because you had q possibilities, but you can't use 0. You can't use this number, and you can't use the negative of this number. So there's 3 forbidden numbers now. So there are q minus 3 possibilities here. Okay. What about the next one? Well, there's q possibilities, but you're not allowed to use 0. You're not allowed to use this one or it's negative. You're not allowed to use this one or it's negative. So that's 5 forbidden things. So q minus 5. Okay, and you continue. Q minus 1, Q minus 3, Q minus 5, Q minus 7, ... What about the last one? Well, it's Q minus, you're not allowed to use 0, so that's 1. And you're not allowed to use any of these 2 times n minus 1 numbers that you already used. So, okay.
Q better not be power 2,
So
right?
that's a very good point. And this is where you start realizing that it is important, and not only in freak examples, but in real examples, it is important that Q should be big enough. If Q is 2, and 2 is a prime, that's a perfectly valid prime. If Q is 2, then this and this are the same equation. Because 1 equals minus 1 in the finite field of 2 elements. Okay? But if Q is not 2, then this argument works out. So that's why you need Q big enough. Cool, so then we get q minus 1, q minus 3, q minus 5, ... up to q minus 2n. And then I get minus 1 plus 2, so we get like this. Okay, and that's the characteristic polynomial of this arrangement. What about the number of regions then? The number of regions is what we get when we plug in minus 1 and we take the absolute value. So minus 1, let's just forget the minuses, right? So minus 1 is minus 2. I forget the minus and I get 2. Minus 1 minus 3, that gives me a 4. Minus 1 minus 5, that gives me a 6. Minus 1 minus 2n plus 1, that gives me a minus 2n. So I get 2n. And so what do I get here? Well, I get a bunch of 2's. 2 times 1, 2 times 2, 2 times 3. So let me take out all the 2's. And then I get 1 times 2 times 3 up to n, so n factorial. Okay, that's the number of regions. Yep. So I said this is 2 times 1, 2 times 2, 2 times 3, 2 times 4, up to 2 times n. And so then I grouped all the 2's together, which gives me a 2 to the n, and then the other ones give me the n factorial. So this is great. It's a beautiful answer. And why is it the answer that we expected? Because we said these were supposed to be signed permutations. How many signed permutations are there? You choose a permutation, and then choose signs. So everything is working out beautifully. Okay. So that's the Bn/Cn case. Now you might find it a little bit awkward that I'm giving 2 names to this arrangement. You don't normally see that in mathematics. Normally things have 1 name. And the reason is that Bn and Cn generally represent different things, but in the theory of hyperplane arrangements, they end up being the same thing. So if you've taken Lie groups or Lie algebras, then, for example, there is a Lie algebra Bn, a Lie algebra of Cn, and they're different. And the difference between Bn and Cn is that one has xi equals 0, and the other one has 2xi equals 0. Okay? So, of course, over the real numbers, we don't care if xi is 0 or 2xi is 0. Those are synonyms. And that's why these two things end up being the same arrangement. But for a lot of other purposes, this 2 is crucial. Okay? And then, for like in Lie algebras or in Lie groups, that 2 becomes very important, and then it gives you a different object. Okay. Finally, so we did an minus 1, we did Bn and Cn, now let's do Dn. So Dn has equations xi equals xj for I different from j, and xi equal minus xj for I different from j. Okay. So again, let's choose a large prime Q, and then we're going to get the number of x1 up to xn in fq to the n, such that xi is not xj and xi is not minus xj. Okay? So the first thing we're going to do is use an approach that doesn't work. Okay, just so you know. This is not going to work, but I want to show you why it doesn't work. Let's try to do what we just did. Okay? How many options are there for this first coordinate? It's not a trick question yet. It's Q. Because x1 could be anything between 0 and q minus 1. I don't have the equation xi equals 0. Here I was not allowed to use 0, but here I am allowed to use 0. Okay. Now what about x2? How many possibilities are there for x2? This is the trick question. Q minus 2? Maybe. Q minus 2 because you had q numbers, but you're not allowed to use this one or it's negative. So q minus 2. But what's the catch? What if I chose 0 here? Then you're not allowed to use 0 or minus 0, but that's only one restriction. So it wouldn't be q minus 2, it would be q minus 1. Okay? So q minus 2 or q minus 1, and then what? Okay? Then it gets a little bit trickier. And so the point is, and that's why I did this example first, because it's easier, because here everything works out like this. Here we have to be a little bit more careful and pay attention to whether there's a 0 or not. Okay? So let's try something different. We're going to split into two cases. In the first case, I don't have zeros. And in the second case, I do have zeros. So if no zeros, how many possibilities are there? And if I have zeros, then how many possibilities are there? So if there's no zeros, then I'm exactly in that situation. Yeah? And so I already know the answer. Q minus 1, Q minus 3, dot, 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 until Q minus 2n plus 1. If I don't get to use 0. Okay? Now, if I do have zeros, then how many zeros can I have? You can only use 0 once, because you're not allowed to repeat any coordinate. So that means that if I have zeros, then actually this is not a plural. This is 1 0. You get to put 1 0 in one position. Okay? So let's decide where we're going to put it. And there's n possibilities for what position that is. Okay? So n choices for which coordinate equals 0. Is it the first coordinate, the second coordinate, and so on. Okay? let's say it's the first one, just for definiteness, okay? Then how many ways are there to complete the rest? Well, the other numbers need to be different from each other. They can't be negatives of each other, and they can't be 0, because you already use 0, okay? So it's exactly that problem again, except now you have one fewer coordinate, and so it's that answer, but one term shorter, okay? So I get q minus 1, q minus 3, and I need to stop one term earlier at q minus 2n minus 1. Okay, which is this last term minus 2. Okay? Q minus 2n, q minus 1, q minus 3. Yeah. Yeah, because the numbers I'm subtracting are getting bigger. 1, 3. The last one I subtracted is 2n minus 1. So I should have stopped at 2n minus 3. Yeah, thank you. So this is minus 3. Okay? So if I... Thank you. I learned something today. You have to distribute minus things. So if no zeros, I get this. If zeros, I get this. And so I need to add these two things. Okay. And the nice thing is that most of it factors. This has to be multiplied by this, right? So n times this. So all of this stuff factors. Q minus 1, q minus 3, dot, 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 up to q minus 2n plus 3. So that's this and that's that. And then I need to add q minus 2n plus 1 plus n. So I get q minus n plus 1. Okay, and that's it. Again, a very nice answer. Very nice and explicit. It factors. And from that, we can compute the number of regions. Okay. So what's the number of regions? The number of regions is the result of plugging in minus 1 and taking the absolute value. Okay. And so that's minus 1 is 2. Remember, I forget the minus signs. Minus 1 minus 3 is 4. Minus 1 minus 2n plus 3 is, it's hard, 2n minus 2. So I factor it as 2 times n minus 1. And then if I put a minus 1 here, I get minus 1 minus n plus 1. So I get n. And I say the same thing. I say let's factor out the 2's. So there's how many 2's? In this case, there's n minus 1 2's, because I lost the last one. I mean, it's basically the last answer, the previous answer divided by 2, right? If I had a 2n, then this would be precisely like before. So now it's that divided by 2. Okay? And why does that make sense? Because we said that they're the sign permutations that have an even number of signs. Now, you either have an even number of signs or an odd number of signs. And the number of permutations with an even number of signs equals the number of permutations with an odd number of signs. Why is that? Just flip the sign of the first thing. If you have something with an even number of signs, and you flip the sign of the first one, it becomes one with an odd number of signs, and that's a bijection between them. And so this is exactly half the number of regions as before. And you saw it in the cube because we had an x in each square. We had 4 little regions in each square, and they became 8 in each square. They doubled. Okay? And that's the order of the corresponding group. Okay? Cool, so that's AN, BN, DN, AN, BN, CN, DN, dihedral group, and now I'm only missing E6, E7, and E8. And the trouble with those is that to write them out is about as difficult as to draw an icosahedron. I mean, they're complicated. They're pretty amazing root systems, actually, and I unfortunately didn't bring down the equations with me. But from the equations, you would never guess that this is finite. And it's very surprising because, again, it only works in 6, 7, and 8. Okay? But basically, the same kind of argument works. And a nice fact about it is that for those guys also, these polynomial factors. It's no coincidence that they're factoring. All of these factor beautifully. And you guys know how rare that is. If you take a random polynomial, it's not going to factor, right? Factoring is like finding the solutions. And you guys know that if you have a big polynomial, there's no method. You can't find the solutions using radicals, for example. But all of these guys have very nice solutions, okay? And that points at some deeper theory in that these numbers actually have meaning. Okay? They have algebraic meaning, which I'm not going to be able to say much about, but that also works out for E6, E7, and E8. I think we're going to stop there. Do you guys have any questions? So what I want to do next time is show you some other nice arrangements, but these are the ones coming from Coxeter groups. So again, if you're interested in knowing more about this, which is a fascinating theory, look up Coxeter groups, and you can find them on stream.sfsu.edu or actually, if you're interested in bibliography about that, I taught a course like that, and there's a whole page of references, so you can find it there. Okay.